All right, so we'll double check that it is actually recording, and then we'll continue. Yep, it is recording. That's good. And then we'll get started. Okay, first thing first, with the homework assignment that is due today. Okay, it is already due.
I thought it was due on the 8th.
There's one due on the 8th. There's another one due today. The first one is due today.
So it's already past due then?
It is already past due. Well, it's a very low point value one. So in terms of affecting your grade, it's not going to make that much of an impact. It's just that I want you guys to have your Linux environment set up and know how to turn in your homework assignments. That's the purpose of the first assignment.
Oh, the test done one?
Yeah.
Oh, okay.
Yeah, but that's due today.
Okay.
That's the one that's due like a few minutes ago.
Okay.
Okay, so you turn that in.
Right.
Okay. So it's not a high point value one. I wouldn't worry too much about it if you forget to turn that one in. Okay. The other one, which is due on the 8th, that one, some people ask me about. Okay, I'll just point out first. Don't worry about the assessment rubric. Okay, that's outdated. So the rubric would say, okay, I'm checking to see if you have a conjunction gate or something like that. Don't worry about it. It is for the previous version of the same homework assignment, so it's not going to be the same for you guys. So I will have to change the grading rubric for your specific homework assignment. So don't read that part. Just turn it in the way you think it is done right. Okay, and then the rubrics will be updated when I grade it. All right. Yep. Go ahead.
You're talking about the lab activity Logisim?
Yep. Logisim. That's the one that I'm talking about right now.
Okay.
Yeah, so the rubric is outdated. Okay, just forget about the rubric. Just do the assignment. Yep.
So just to be clear, you want us to do it per the equation as it is?
Yes.
Okay.
I know the equation is kind of strange. Okay, the out two ors,
okay.
But there are nots. Okay, there are negations within those things too. All right. So last time I demonstrated in class of how to mess up a program, right? Okay, I demonstrated two programs that are both messed up. One would call a subroutine, but when the subroutine returns, it will return to another subroutine that is never called anywhere in the program. Do you guys still remember that one? Okay. No? Yes? Sort of? Well, if you don't remember, it's okay. It's recorded. It's on YouTube. Okay. The other one was it calls a subroutine, but when the subroutine returns, in the main function, everything is shifted. Okay, I made it shift by 4 bytes first, so it is like shifting whole variables first. But later on, when I made it shift by 2 bytes, then it has corrupted values because the boundary of the variables are no longer lined up, so they are not even entire variables in that case. In other words, what is happening? If you want to draw a picture, it's like this. In terms of memory, okay, if you have x, y, z as variables, and each one has 4 bytes, okay, so I'm just using the subtension, as a byte boundary, okay. This is how x, y, z are supposed to be. But if you change something with the stack, okay, which in return would change, what we call the base, the frame pointer, okay, the frame pointer, then it will end up to be like this, okay? It will end up like this. It will interpret these 4 bytes as x, these 4 bytes as y, and these 4 bytes as z. So that's why those values are all kind of funky when I mess around with that stuff, okay? I cannot really explain that at this point in the class, but at the end of the class, if we look back at the end of this class to these examples, all of you will be able to go like, oh, I can explain that. That's pretty easy to explain, okay? That, I think, is the value of this class. On top of that, the other part of this class would be the computer architecture stuff. Why do you want to understand computer architecture or computer organization? Because it's in the transfer degree, right? Okay. But why do you think 4-year universities want you to understand that stuff?
For efficiency.
for efficiency, but you also want to know what is under the hood, okay? Even though if you're on a computer science track, okay, it really still helps to understand, the underlying, operation of a processor, okay? Because there are things that are changing, okay? Microcode, can change now. For many processors, you can actually modify the microcode. So we'll get to that, later as well. All right, so we are pretty much done with 4-bit adder, okay? We talked about it in class. I also demonstrated in class how to create basically hierarchical structures using LogicSim, okay? So that's what you need to do with your 4-bit adder. The next homework assignment is the 4-bit subtractor, and I have a due date assigned for this already, which is 2 days after the adder. Let me just double check. So it is due on the Thursday of September 10th, so it is 2 days after the adder. When you're working on the adder homework assignment, if you just keep in mind the subtractor homework assignment, you can pretty much get both done at the same time, okay? Because they are very similar in terms of structure, and the subtractor turns out to be easier, okay, in terms of number of gates. Okay, if you have done it or look at the equations, you will know what I'm talking about. If you have not, just go ahead and take a closer look at the equations. Okay, what is the equation of the R? What is the equation of the borrow? Okay, and you will find similarities, and that similarity will let you design a subtractor using fewer gates compared to an adder. All right. So with that out of the way, we are going to move on to the next main topic. The next main topic, has to do with a guy called von Neumann. Okay, and is John here today? Nope, John is not here yet at this point. But John would point out, the name is not von Neumann; it is von Neumann. Okay, so the pronunciation is von Neumann. In many classes, when I took, the equivalents of this class, they just talked about the name and what it is, but they never really talked about the person, okay, von Neumann as a person. So I would just kind of point out, or spend a little bit of time, not a whole lot, to talk about von Neumann as a person. So when you look at von Neumann, he has a really big entry in Wikipedia. This guy is a genius. Oh, here comes John. But this guy is a genius. Not only is he a genius, he is a genius of geniuses, or genii, I suppose. Okay. He was actually working in Stanford as a professor in the same time frame, or at least it overlaps with Albert Einstein. Okay. And when he works, he likes to listen to music, loud polka music. And Einstein hated that. And they were in the same hallway. So you can kind of imagine the kind of chemistry that goes between these two. But he is respected by a lot of other scientists. But you can basically say, you can read just this part here. He made, okay, let me just kind of zoom into this part here. He made major contributions to a number of fields, not just physics, not just mathematics, not just computer science. So in mathematics, physics, economics, computing, and statistics. And each one, subdivides into, subdivisions of that field. So he is just a generalist, okay? He is not just, someone who's focusing on one little thing and be very, very good at it. He is just good at everything. Unfortunately, the guy passed away pretty early too. So that part he is kind of, about the same. Well, he actually passed away quite a bit older compared to Turing. Alan Turing passed away or committed suicide, or allegedly committed suicide when he was in his 40s. Okay, when he was about 40 years old. This guy passed away when he was only 53, and most people believe his cancer had to do with his participation in the hydrogen bomb experiments. So he was actually a part of the H-bomb or the hydrogen bomb experiments as well. So So anyway, interesting person, and I think, it would not hurt to read a little bit about his bio to kind of understand, what kind of a person came up with the idea of a von Neumann architecture. All right, so back to the von Neumann machine. So before we talk about, the modern day von Neumann architecture, it really is helpful to remind ourselves of older computers, okay? The question is, with these older computers, they are very specialized machines, okay? They were built to do one thing. And it's very difficult to have the computer or these mainframes to do something other than what they were designed to do in the first place. So what we'll do is we'll just read this a little bit here. In the Colossus, programming Colossus was done by setting switches and plugging appropriate units together. In other words, you are actually going into the chassis, okay, with lots and lots of wires going in every direction. And you have to physically rewire the components inside the computer in order to, quote unquote, reprogram the computer so that it would do something other than, something that it did before, okay? It's not just like, when you guys say, oh, I want to download a new app, or there's an update of Android. What do? You click a button on your screen, and it's all done, okay? And then people complain, they're like, oh, it's so slow, it takes about 5 minutes. Try rewiring these boxes. Okay, and there's no double checking either, okay? The computer is not going to tell you, oh, this wire cannot go here, or it's not supposed to go here. All right? I mean, with your Android updates, sometimes the checksum doesn't work out, and your recovery will complain about it and go like, no, we're not going to update because it doesn't check out, right? Not with these things. If you wire it up incorrectly, it can potentially actually cause your components to fail. Okay, so that's the Colossus. And then later on we have the ENIAC. The ENIAC can be programmed to perform complex sequences of operation. So it has loops, branches, and subroutines, kind of like modern day computers. But the task to take a problem to map it onto the machine was complex, and usually it will take what? Weeks. Okay. And back in those days, the complexity of the ENIAC would be about the same as, well, it's not even comparable to an Apple II computer from the 80s. Okay, and those things only have 64 kilobytes of RAM. So the longest program you can write is only about 30 kilobytes or so. These are much less complex compared to an Apple II computer, but it will take weeks to reprogram it. Okay. That's because the program has to be figured out on paper. The process to getting the program into ENIAC is by manipulating its switches and cables, and could take days. So you first have to plan it out on paper, and then just to implement, just to quote unquote reprogram, or in your terms, because I know you guys know these terms, just to flash it, okay, would take days because it's all manual. All right. And then after that, it has to be followed by a period of verification and debugging. Because what if someone did not follow the piece of paper correctly and miswired something? Then it won't work correctly. So you have to debug it. Until this guy came along, okay, this is von Neumann. When he came along, he go like, hey, since we can store data, okay, the information or the numbers that is being crunched and processed, we can store that in volatile memory. Why can't we store instructions in volatile memory as well? Okay, so before, there's a clear distinction. Okay, if you look at the computer architecture, there's a straight line, dividing two halves. One side is, controlling the behavior of the computer. So this is, and the other side is basically the memory of the computer, the working memory. In other words, these are the numbers that are being processed, okay? The summation of something, the standard deviation of something, okay? The sum of, the sum of x squared in statistics, that's the working memory. But the logic, or what determines the behavior of the computer, is on the other side, okay? And this is hardwired in the past. This is hardwired, literally wired. Okay, not it's literally hardwired. This is actually stored in random access memory or some kind of memory. Okay, it may not be random access, but it is some kind of memory. It is volatile, which means if you turn off the machine, it's all gone. Okay, when you turn the machine back on, it will get initialized, and depending on the behavior of the computer, it will get changed as the program executes. So this is the old way of doing things. What von Neumann is saying is, why can't we put this block over here as well? So it's no longer hardwired. Instead, it is living in memory that can be changed at runtime. So there won't be a whole lot of rewiring. Okay? Are there any questions about this kind of? I would say this is a revolutionary change in the history of computer science, because without this change, okay, all the subsequent changes to computer science will come really slowly. But because of this, we can reprogram computers a lot more effectively, and that's why that's how we can kind of move on to the next generation quicker and quicker. Are there any questions about this picture? No, there's no question about the picture. Okay. All right. So that's the whole idea of the von Neumann architecture. Now, after that, we have the usual Linux commands that I have demonstrated already in this class. Now, LogicSim has its own RAM module. Okay, so this is an explanation, or more like a duplication of the online help of LogicSim, because LogicSim actually has a fairly good explanation of how RAM functions. Okay, RAM is kind of the centerpiece of the von Neumann architecture, because when you look at a modern computer using the von Neumann architecture, we have memory. RAM stands for random access memory. Okay, so next to the RAM, we have what we call the CPU. This term has changed from time to time. In the past, people have just called this the processing unit, and now we call it the CPU, the processor. There are multiple names for this thing. But these two interact in many ways. Oh, that's an arrow right there. Okay, so these two components interact a lot, okay? And that's because whatever program or the instruction that the CPU needs to read to execute is coming from RAM. But that also applies to the data that is being processed by the processor. So RAM is now serving two functions, just like in this picture. It is storing both the numbers, the data to be processed, but it's also storing the instruction that tells the processor what to do. Okay? So that's why it is important to understand, how do we interface with RAM, or random access memory. Now this is really just a explanation of all the ports of the RAM module. So you need to read this stuff here, or the online help of LogicSim. What I'll do instead in class is to show you in LogicSim, how to design a small experiment just to play with RAM. How do I read from a certain location? How do I write to a certain location? That's what we're going to do today. Okay? Are there any questions about all the stuff that I have talked about so far? No questions? All right. Okay. Then we'll go ahead and start up a LogicSim, and then we'll take a look at the RAM module and how to test it too. How do we design a small thing to test the RAM modules, just to understand how it works. So LogicSim. And before I actually play with a RAM module, I'll point out where to find the online help. So you go to online help here and go to library reference, and then you go to memory library, and then go to RAM. And this is the online help of LogicSim. It's built into LogicSim. If you have installed it on your computer already, you have this already. Okay, so this is a really good explanation already. But since you can read this part, prior to the class or after. Okay, but what I'll do today is I'm actually going to design an experiment to play with this. In fact, I'm going to implement something like this. Okay, and as I connect pins, quote unquote pins, to the ports, I'll explain what they mean. Yep.
Is this the same thing that you have on Moodle, or is this deeper?
The stuff that I wrote on Moodle is specific to this class, specific to the content of this class. This is not intended for a particular class, but it does explain fully how to use that component. So you can use this as reference material, but what I wrote may be a little bit simpler, but it's more tailored for this class. Okay. All right, so I'm going to close the help window. I just want to show you where to find it. And what we'll do is we'll just go ahead and put that component onto the screen. So I'm going to pick a RAM module and put it here. Okay, the first thing we want to do with a RAM module is to understand how many ports does it have. A port, P-O-R-T, is basically one or more pins, okay, that serve a particular function. So it doesn't have to be exactly 1 pin per port. It can be like 8 pins per port. But those pins collectively performs a particular function that is specific to this module. Okay, so that's what a port means. If you hover the mouse pointer over a particular port, it will tell you what it is. This is the address port, okay, or the address bus, okay, it connects to the address bus. This is the data bus, okay, or data port, value loaded or stored. This is the chip select or the select port. This is the clock line, okay. This is the load port, which controls either are we reading or writing. And this is the clear, which is to reset the content of the memory module, okay. All right, so the best way to imagine this is to think of this memory module as a binder, okay, as a binder with pages and pages of papers, okay. All right, so what is the address bus going to do? The address bus tells you, or tells the module, which page to turn to. So the address bus will basically specify, oh, I want to address location, blah, blah, blah. So the memory module will turn to that page. But what are we going to do to that page? Are we reading the content from that page, or are we writing new content onto that page? That is controlled by this particular pin here, or this port, which is called the load port, which is kind of an awkward name. Most people would call this the read-write pin, okay? Because it does specify a read or a write operation. So depending on whether it's a read or write operation, what you are going to do is either to listen to somebody else that will tell you, oh, I want to overwrite the content of this page to blah, 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 blah. So that will be a write operation to the RAM module, okay? Or if it is a read operation, then you are going to read out the content of that page and say, oh, the content of this page currently is blah, 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 blah. So the way you talk to whoever is, or the way you listen to or you talk to whoever is on the other side is done by the data bus or the data port. Are we still doing okay so far? Okay. So these two are distinct, okay? The one port specifies which page you want to address. The other port will basically be responsible to communicate the content on that page. Now this design is, yep, go ahead.
So the address port is getting its page instruction from where?
From the processor.
So the processor is saying, I want to look up page 5, and then where does it go to look up page 5?
It's inside this particular thing.
Okay.
So when the address bus is active, the memory module will listen to it, but it may not do anything because if the select port is not asserted, then the memory module will say, oh, you're not addressing me, you may be addressing somebody else.
Okay. So it sends it out to all the RAMs, and then
Correct.
the one that gets the
Yep, absolutely. So now we're going to make this problem a little bit more complex by having another RAM module put right here. Let me think about it. Side by side or next to it. Well, this will work. Okay, I just need to zoom out a little bit here. Okay. It is impossible to use one single memory module, physical chip, to implement all the RAM that you need in a computer. How much RAM do you have on a medium-end computer these days?
4 gigs.
8 gigabytes, right? Well, it's impossible to make one single chip that has 8 gigabytes. It's just not possible. Okay. So what do? Well, we have. Has anyone looked at what a DIMM looks like Okay, DIMM, D-I-M-M, which stands for Dual Inline Memory Module. Okay, so what do you see on a DIMM?
See connectors.
Well, you see multiple chips. Okay, the number of chips depends on the density of the chip and what is cheap at the time. Okay, but you see multiple chips, and that's what's happening. Okay, you cannot implement all the memory that is needed on one single chip, so you need multiple chips. Okay, but now the question is, with all the multiple chips, how do we coordinate and say, okay, which content comes from where? That becomes the next question. Are we doing okay so far? The first thing that is really kind of confusing to someone who's new to this type of thing is the address bus is shared. If you have 16 memory chips, they are all shared. And then the other part is the data bus is the same way. If you have 16 chips, then you still have only one data bus. The reason why we call this a bus is because it's not just one single wire on the motherboard. It is actually a whole bunch of wires, depending on the width of your memory system. If you have a 32-bit memory system, there'll be 32 wires coming out of each chip corresponding to the data bus. Okay. What other wires are shared? The clear wire is also shared. So I'm going to try to do this in a way that is easy to read. Okay. Do you guys notice the color is changing? This is in blue instead of black.
Yeah.
That's because it is a single pin. Okay. The other one is the width depends on the address bus. Okay. This is a single pin. It's an actual single wire. Whereas the black lines are representing multiple wires. It's a bundle of wires. Okay. The load line, the read-write line, is also shared because you are actually using multiple chips to implement one single memory system. So if you're reading all the, potentially all the chips. When you're writing, you're also writing all the chips. The clock line is also shared. The clock line is basically needed to perform a write operation. So a write operation occurs when the clock line is having a falling edge. Okay. The only one line that is not shared is the select line. The select line let you basically say, I'm talking to you, the first memory chip, or I'm talking to you, the second memory chip. So let's put some labels on the chips, just so that we can easily identify which one we are talking about. So we look at this one, and it doesn't have a label for me to, well, I suppose I can just put an actual label here. So I'm just going to call this RAM 0. Okay. Remember, in computer science, we like to start from 0, but it's for good reason. Okay, so we have RAM 0 and RAM 1. All right, so what you want to do now is to imagine each chip is one person with a binder. Okay, so we'll just randomly pick two students representing the two chips. Okay, together they are representing the entire memory system of the entire computer. All right. But the processor is going to say, the processor will look at the total capacity of both chips as one single linear space. Is that okay? So we'll just kind of use an example here. You are responsible for page 0 to 49. You're responsible for page 50 to 99. Okay? So together we have a capacity of 100 pages. Is that okay? But that's only from the perspective of your program. From the software program perspective, you are looking at a memory range of 0 to 99. But to each memory chip, each binder is only numbered from 0 to 49. Are we still doing okay so far? So there's a little mismatch, okay? So between the processor and these two memory chips, there is what we call a memory management unit, MMU. So the MMU will take the logical address and figure out how to talk to the two memory chips in a certain way. So it will basically say, for the first 50 pages, I will go to the first chip, RAM 0. For the second half, I'll go to the second chip. And it will do the translation as well. So page 64, for instance, will translate to the second chip, RAM 1, but which page on RAM 1? Remember, RAM 1 starts on page 50. It'll be page 16. Yeah, it'll be page number 16, but it's starting from 0. Okay, so that's the job of the memory management unit. Okay, it will do the quote-unquote translation and only get through. It will only address the memory chip that needs to be addressed. So when I say, oh, give me so as a processor, I'm just going to say, give me the content of page 64. Okay, in between those processor and the memory chips is the MMU. So the MMU understands how I'm dividing up all the memory chips, and it will go like, oh, page 64 is found on RAM 1. So it will assert the chip select line of RAM 1, and it will also do the quote-unquote translation and say, oh, page 64 from the processor's perspective is actually page 14, okay, on that particular chip. So it will put out 14 on the address bus to specify page 14 on that particular memory module. Are we doing okay so far with at least just the concept of what an MMU is supposed to do?
So how does it? So how does well, I guess are you going to explain the memory managed unit?
Yep. It's fairly easy, okay, because there's one component that can do all that. So what we'll do is to move all of this a little bit lower, okay, just so that we have some room for the MMU. So what the MMU does is a fairly simple thing. All it needs to do is what we call a decoder, okay? So what we'll do is we're going to go select a decoder from plexers, okay? So a decoder looks like this. Okay. And with this decoder, we do not need, there's no tri-state, disable output, floating, including enable. We'll just say no. We'll simplify the design of a decoder, okay? All right, so we'll take a look at the decoder, and select bits is 1. That's okay. That's fine. All right. So this is a decoder. We'll go ahead and magnify a decoder just to take a closer look at this particular module. A decoder has 1 pin. Okay, come on. Tell me what it is. Yeah. This is output 1. This is output 0. This is the input. Yep, go ahead.
So basically, the decoder helps to communicate with RAM from processor to RAM?
No, a decoder is actually a very simple device, okay? But it does serve the purpose of what we need to do, okay? A decoder is nothing more than indexing, okay? So you're basically looking at indexing here. What I have highlighted here on the screen is the input, okay? Now in this case, I have a single input, or if I click on the chip itself, it will show that I only have a 1-bit input right here. Select bit is only 1. So we have a select bit. It is, since it is 1 single bit, how many values can it take on? What are the possibilities for this particular bit, which is an input?
1 or 0.
0 or 1, okay. This is 0, this is 1. So now we want to look at output 0 and output 1. So we want to look at output 0 and output 1. Okay. When the select bit is 0, out 1 is a 1. And out 0 is a 1, and out 0 is a 1, and out 1 is a 0. When select bit is a 1, it will do the other one. It will basically say, this is a 0, and this is 1. That's the behavior of a 1-bit decoder. But in general, we also want to kind of understand what a 2-bit decoder is going to do. It's actually not too difficult. So we have select bits in this case because there are 2 bits. And then we have 4 outputs. Out 0, out 1, out 2, and out 3 in this case. I think most of you know where this is going, okay? 1 and only 1 of the outputs will be a 1, depending on what the select bits are. Is that okay? So, but we'll go ahead and enumerate all the possible cases. 0, 0, 0, 1, 1, 0, and 1, 1. When the select bits, which are the input into a decoder, are both zeros, out 0 is a 1, everything else are zeros. When the input bits are is 0, 1, then out 1 is the only one that is a 1. Everybody else are zeros. when the input is 1, 0, can someone tell me which one is a 1 and the rest are zeros? Out 2 is the one that has a 1. Everything else are going to be zeros. And the last one, quite obvious, like that. That is what a decoder does. Okay, it looks at the input bits, and it will turn only one and only one of the output to be a 1, depending on the value of the input. That's called a decoder. Yep, go ahead.
This might be off topic, but is it a coincidence that those are all always an identity matrix for the output?
You are absolutely right. That's a good observation. If I make a 3-bit one, then you will have you'll have an 8 by 8 table, and the diagonal this way is going to be all ones.
So that come up again at some point.
Well, if you want to look at this from the software perspective, I can tell you the software perspective what it is. So we'll go and take a look. I'm just going to use a mouse pad here. Okay, so I'm going to show the diagram on one side, but I'll give you the software perspective. From the software perspective, so we'll just say, okay, there's only one input. Okay, so in, okay, int in. Okay, that's a variable controlling the input. The output would be an array of booleans, right? So boolean out, and that's going to be dependent on the width of in. Okay. So if you remember in C syntax, you can specify in a structure, you can do this. You can specify in to have a certain number of bits. So let's say this is n bits here. So the output is going to be 2 to the power of n. Because with n bits, you can control 2 to the power of n individual bits. Are we understanding this part okay? 2 input bits, 4 outputs. 3 inputs, 8 outputs. 4 inputs, 16 outputs, and so on. Are we doing okay? So the logic to do this is basically saying, out bracket in is the only one that gets a 1. Okay? So for everybody else, okay, let's put this in the loop so we can see it. So for int I is 0, I is less than 2 to the power of n. I know this is pseudo C, but just bear with me, okay? There's no such operator in C. I just use it as 2 to the power of something, okay? Fine, you don't like this? I'll change it. How's that? Should be a 1. Yeah. So n is just a macro. Would that work? Right? Left shifting is the same thing as 2 to the power of something. How many people have never seen the left shift operator?
Not used in exponents.
Well, because left shifting is shifting, whatever bit pattern, the number of bits to the left-hand side. So it's the same thing as doing 2 to the power of something, because we're dealing with binary shifting here. Okay? All right, so now we can say, okay, what is the output corresponding to I? Out I equals 2, okay? And I'm going to use a ternary operator here, okay, just to test whether you guys still remember what a ternary operator is. So one is going to be true, the other one is going to be false. All right, so what determines whether it is true or not is easy. Is this in? Now, obviously, I have made that mistake many times in my programming career, okay, and it ends up with mysterious behavior of this program. Okay, but this is basically what it is. If I want to describe what a decoder does, that's what it does. Okay, you have one single input that can be multiple bits. Okay, you have to determine what is the width of the input. But once you have determined the input only has n bits, then we have 2 to the power of n output pins. Out of those pins, one and only one is going to have an output of 1. Everybody else is going to be a 0. The one that has an output of 1 is basically, when you look at the indexing, it matches the value of n. The value of in, not n, but in. In is a variable. Is that doing okay so far? Sort of? Sort of? Okay. Now, the other thing you can also do, which is fairly easy to do, is just to play with it, okay? So this is something that you probably want to learn how to do too, is, okay, I think I have a good understanding of what a decoder is, but I want to test it. I want to see what it does, okay? Well, go ahead and do it, okay? 1 bit may not be enough to show you. Let's deal with 3 bits, okay? This is a 3 input bit decoder. And what we'll do is we're going to connect input pins to the input, and then we'll have output pins corresponding to the outputs. This will basically give us the ability to visualize what is the behavior of a component like this. Oh, no, get rid of this. Okay. I just want to select that wire, but it won't let me do it. There we go. Get rid of 1. It's rather stubborn. Well, this is not too bad. I used to work with circuit layout, software, which is kind of what we are doing here, and this is not bad at all. Trust me, there are much worse, interfaces. So Control, paste. You can kind of see what I'm doing here. I'm trying to be lazy because every time I'm doubling the number of pins. There we go. Okay. First thing first, let's connect the input pin, and we're going to have a problem here. Bing. Okay, when you see this color, the kind of orange color, it's telling you we have a problem. It actually tells you down here, it says incompatible widths. That's because the input is 3 pins, okay, has 3 individual wires, but this only has 1 individual wire coming out of it. So it's not matching. But that's an easy thing to fix, because what we need to do now is to click on the input pin itself and say there are 3 data bits in the input pin. In other words, the word pin in this particular software is somewhat of a misnomer because it's basically a port, okay? It's an interface to something else. Are we still doing okay so far with this? So now the rest is really just going, this is output 0, this is output 1, output 2, output 3, output 4, output 5, 6, and 7. Okay? This is the input. Input is 0, 0, 0. And that's why only output 0 is asserted, has a value of 1. Everybody else has a value of 0. Okay? I'll just test your knowledge, or test whether you can apply what we have just learned. What if I want this pin to turn into a 1? What do I need to use as the input? Well, first of all, you have to count, okay? What is the number of this pin?
6.
6, okay? How do you represent 6 in a binary number? 110, okay? Well, let's try that. So we'll go ahead and specify 110. I think you can just type it or not. We have to turn into the simulation mode. Then we can specify 110. Well, that's actually not 6. That's actually 5 because we count from 0. That's right. So, well, that's easy to fix. That's 5. Okay. So are there any questions about what a decoder is, what it does? No? No questions? Yep, go ahead.
Okay, so how do we connect this decoder to RAM 0 and RAM 1?
Well, we don't need something this complicated, okay? So let's take this away. Okay, we don't need this one anymore. This is really just for demonstration, okay? Yep, go ahead.
So it's 3 inputs. So we have 8. Why do we have 8 possible outputs again?
2 to the power of 3 is 8. That's fine. All right. So, but we don't need something this complicated. All right. So the first thing we want to do is to look at our current memory system, and we want to say, okay, but how many bytes do we have, combining 2 memory chips? So what you need to do is now take a look at the properties of RAM 0 and RAM 1 is identical. Okay, so that's what you just need to look at. 1. You can see the address bus width is 8. Okay, So with 8 bits, how many locations, how many unique locations can I address? It'll be 2 to the power of 8, which is 256. That's right. So the address bus determines how many unique locations can be addressed. And the answer is 256 per chip. Okay, so each chip, RAM 0 has 256 locations, and RAM 1 also has 256 locations. Together, we have 512 locations. Very good. What about each location? How wide is each location? That's your data bit width. So in this case, we have 8 bits per location, which is 1 byte. So that means RAM 0 implements 256 bytes of memory, and RAM 1 is the same way. It implements another 256 bytes of RAM. Are we still doing okay so far with how to read off this thing? All right. So together we have 512 bytes, okay, in this particular system. With 512 bytes, how many bits do you need to address a unique location? If you look at all 512 bytes as one single space, okay, how many bits do I need to address, a unique location? 9 bits. Very good. Okay. So what we'll do next is to implement, or is to put in the input pin for the entire memory bus. Okay, 9 bits. So we are going to change the data bits from 1 to 9. Okay, and we just have to. Why is the 9th bit up here? I suppose we can change the font size to try to make it all fit. Nope. That's just label. It just doesn't look very good. I'm trying to make it look a little bit better. Nope, it cannot be resized. Well, I guess we'll just have to do it this way. If there are 9, yep.
Oh, why is it 9 bits again?
Because 2 to the power of 9 is 512. Okay? So the first thing we want to do is to say, I don't want all the trouble of what MMU, the MMU thingy. So I'm just going to hook up this interface directly to here. What do you think is going to happen when I make this connection to here? There'll be an error, but what kind of error am I going to see?
Too many
Mismatch, okay, incompatible. Because the pin, the rectangular box up there, has 9 individual wires in the bundle, okay? But this only has 8 individual wires in the bundle. They won't connect, okay? It will complain and go like, nope, this won't work. But some of you will say, Tag, I need to see it to believe it. Okay? Orange wire, clearly indicating incompatible with. This is 9, that is 8. Okay? So it's not working. Well, okay, if it's not working, that means we really do need a memory management module to help us get this to work. So what are we going to do? What we need to do is to take the most significant bit of this bus and say, you are not going straight into the address bus. Instead, you are going to a decoder, and then the output of the decoder will go to the select line. Okay, so let me just hook up the wire and you guys can see whether it makes sense or not. Okay, but how do we pick one wire out of a bundle? Remember, this thing here, okay, what I have just highlighted here, is a bundle. It's a bundle that has 9 individual wires. And what I need is just 1 out of the 9. Okay, so what I need is a splitter. Okay, and there is such a thing in the design here. You go to wiring, and then you just need to find a splitter. And we put a splitter here, and just to make the design look a little nicer, I'm gonna change it a little bit. Okay, so we'll hook up a splitter to the bus, and obviously it's going to complain because the default splitter only has 2 wires. Okay, bit within is only 2, so I need to change that. Okay, I need to change it to 9 to match up with this pin here. So I will change this to 9 so it doesn't complain about it anymore. But the way that it splits by default is about half, as the top one and about half on the bottom one. So when you read this part here, it's basically saying bit 0 to bit 4 is this bundle, and then bit 5 to bit 8 is the bottom bundle. So I have separated one bundle into two bundles. Okay, the first bundle will have 5 wires going from bit 0 to bit 4, and then the second bundle has 4 wires going from bit 5 to bit 8. Is that how I want to split it?
No.
No, I want bit 9 all by itself, and then the rest still remain as a bundle, right? Well, let's see how we can do it. Click on the splitter, and now we can select, okay, which ones are belonging to the top one. Now, you can kind of do the interleave thing, which is really kind of funky, okay? You can do it, but that's not what we need to do right now, okay? So what we need to do is to put everything to the bottom except for bit 9. So we'll, well, I suppose we can do the same. We can do the reverse. Everything belongs to the top except for the last one. There we go. Okay, so this is a good way to split it because bit 8 is now on its own, having its own very own wire. And then all the other wires, bit 0 to bit 7, is on its own bundle. Are we doing okay so far with this? So what we do with the top part is easy. So the top part turns out to be the easy one to deal with, and I'm going to go all the way around here because I need something else for the other one. Okay, there we go. Not a problem. Okay, what about bit 8, which is the most significant bit out of the 9 bits of the input?
You said decoder, right?
A decoder, exactly. So we'll go pick up a decoder, and the decoder belongs to the plexers. So we pick up a decoder. We change it a little bit so that enable is not there, just to simplify the design. And then we just take this bit here and hook it up to the input. Now, once this is the input, we have 2 outputs. Where do you think I should connect output 0 and output 2? Output 0 and output 1 to? Yep.
So bit 9 is always the most significant?
Bit 8 is the most significant.
All the time?
Well, okay, when you connect something to a splitter, you are going to, you basically say, okay, which one is going to be the most significant one. In other words, I could have flipped it, okay, and it would still work. But I just want this to be consistent. So I'm using bit 8 as the most significant bit.
Okay.
All right, so what do we do with out 0? It goes to the select of RAM 0, okay? So we'll go ahead and make the connection. Now obviously, if my screen is bigger and I can run at a higher resolution, I don't have to scroll around all that much, but that's okay. We'll just do this. And hook this one up to RAM 1, or the select line of RAM 1. All right. Is that making any sense? Go ahead.
So the CPU is processing 9 bits.
Yes.
One of the bits is dedicated to the selection.
Well, the CPU doesn't care, okay? The CPU, which is running instructions that you specify as an assembly language programmer, does not really care how memory is divided up into components. So it can be 2 256 byte chips, can be 4 128 byte chips, it can be configured in any way. The MMU, which is what we are doing here, is the one that is responsible to split up the address line coming out of the processor, feed a portion of that through decoders, and then the other portion straight into the address bus.
Okay.
That is the job of the MMU.
Okay, so to the left of the decoder is the MMU.
The decoder is a part of the MMU.
Okay.
The splitter and the decoder is basically our MMU here.
Okay.
So if I want to document this and identify which part is the MMU, I can do that by drawing. I think there's a way to draw something. Maybe not. Nope. Okay, but basically it will be this part here. This is the part that is serving as the MMU.
And what's the box to the left?
The bottom,
The
this
box
part
to-
here.
No, the box to the left, the 9-bit.
Oh, this one?
Yeah.
That is representing where the processor is connecting, how the processor is connecting to the address bus of the memory chips. Okay. All right. So now that we got this part done, let's deal with.
One more question.
Yep.
Alright.
Mm-hmm.
So to read the bits right there as an input, we'll go from top to bottom, right?
This is the input.
Yeah.
This is 0. This is 1.
Okay. I'm talking about the box though, the very.
You're
first.
talking about the what? Oh, you mean this one here?
Yeah.
Oh, that we can try. Okay, so take this one to be a 1. So that is actually, this is actually the most significant bit. This is the second. So you read from here, 0, 1, 2, 3, 4. Because if I click on this one, the other chip is selected.
Okay.
Yeah.
Thank you.
So this is actually bit 8, this is bit 7, and this is all the way back to bit 0. Yeah. Okay. Alrighty. Any other questions before we move on? Yep.
Oh, so what are those numbers in the RAM doing?
The numbers?
Yeah.
Well, that's the content of RAM. Okay, so right now we're not too concerned because I have to finish up the whole design first. Okay, so we still need to expose these lines to pins so that we can control these. But since I have most of it up here, I'm just going to move all the wires up here too. So let's go ahead and do a few pins here, and this time I'll make it face south. Okay, there we go, and do a Control C, Control V. I'm just replicating 3 of these. Okay, there we go, and I'm going to label these so that we know which one is which one. So the first one is going to be our clock. The second one is going to be our load, and the last one is going to be our clear. CLR. And then we'll just make connections like that. Okay, so this is going to the clock line. This is going to the load line, which is down here. And this is going to the clear line, which otherwise is usually known as the reset line. Okay, there we go. So now we have most of the ports of the memory chips connected, except for the data bus. So I'm going to make one for the data bus as well. So let's see, where am I going to put that? Well, I can put it here, or I can put it here. But it's going to be an output pin. Well, it's kind of, it can tri-state, okay? We'll talk about that in a little bit. It's both output and input, so we'll do both of those here. And it's going to face west. All right. And how many bits do we have for the data bit?
8.
8. Yep, 8 is correct. So we'll put 8 here, and we'll put 8 here as well. Okay. I'm going to do the connection later on, but because it depends on whether we are reading or writing. So we're going to do this. All right. Okay. So this wire has to connect to one of these things. So I'm just going to show you how to write the content to memory first. Okay. So this is what we'll do. If I'm going to write to memory, should I use the rounded corner pin or should I use the square one?
The rounded. Square.
The square, because the square specifies input, because that's what we want to do. We want to specify the content on the data bus. So it will be this guy. Okay? So we're going to make a straight connection like that. Okay? And now we can specify a write operation. Okay, so let's go ahead and work out some math here. Okay, we want to work out a particular location, a particular content to write to it, and then we want to see how to make it happen. So let's say we want to go to address, logical address. Okay, this is before the MMU. So the logical address, we want it to be 300 in decimal. Okay, so 300 in base 10. And the content to write to that location, I want 98 in decimal. Okay, that's how I want it. This is the operation that I want to do. write the content of 98 in base 10 to location 300 in base 10, and this is seen from the software or instruction perspective before the MMU does its trick. Is that okay?
So,
All right.
so we're saying we're taking the number 98 and writing it to the address 300.
That is correct. But those are all in base 10, so we have to do some base conversion here. Okay? First thing first, okay? We know that we have to go through the decoder, right? Now you can convert to base 2 first, or you can do it later, okay? Because we know we have to address RAM 1 and not RAM 0. So you can do base conversion first or not. How do you do base conversion from base 10 to base 2? Well, you can pull out your calculator and do it, okay? But what if you lost your calculator, okay? Can you do it by hand? Okay, so we look at 300. It has one 256, right?
Yes.
And once we take up the 256, we'll have 44 left, okay? So with the 44, we have a 32, so that will have 12 remaining. So then we have 8 and a 4, okay? So looking at this is still in base 10, okay? But all the components are already in binary, or in powers of 2. So now we can say 4 is 100 in base 2, 8 is 1 followed by 3 zeros in base 2, 32 is 1 followed by 5 zeros in base 2, 256 is 1 followed by 8 zeros in base 2. Because the number of zeros is really just the power in base 2. Okay. All right, so now we really do have a base 2 number because it is 0, 0, 1, 1, and then a 0 and a 1, and then a bunch of zeros and a 1 down here. So I just have to count the right number. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay, so this is the address. Good. Because now we can set the address bus, right? So let's go into simulation mode and set the memory bus or the address bus to 1, 0, 0, 1, 0, 1, 1, 0, 0. Okay? The processor is going to do exactly the same thing when it needs to write to a memory location. Okay? It will specify in the address bus to the MMU. The MMU will do its own little trick. So now we know that this chip is selected and the location is 2C in hexadecimal. It's already getting to the right location. Okay? Now we have to specify the actual content to write to that location. The content is 98, right? So 98, we have to do another base conversion here from 98 to binary. So 98 is
64.
There's a 64, there's a 32, and then there's a 2. Okay? So now we have a 1 0 in base 2, we have a 1, 5 zeros in base 2, and then we have a 1 followed by 6 zeros in base 2. So this is 0, 1, 0, 0, 0, 1, 1, and then another 0. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there are 8 bits here. Okay. Are there any questions about this base conversion? Remember what I said? If you know how to make exact change using the least number of coins and bills, you know base conversion. That's basically what it is.
Shouldn't have one more 0 in the front?
Yeah? No, I think that's right. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 bits here. Okay, so let's put that into here. 0, 1, 1, 0. And there's another one here. Okay, there we go. So this is what the processor has to do. It has to set the address bus. It has to set the data bus. Now we have to convince the chip that is selected and say, yes, I want you to write this content into your binder. Yep.
I'm sorry, I know you're recording this, but can you show the input first?
The input to
The 300.
the 300.
Yeah.
That's up here, over here.
Okay. thank
It's
you.
1 0 0 1 0 1 1 0 0.
What if you needed to access a number outside of that, outside of that scope?
Then you ran out of memory because you only have 12 locations. Okay, so now we want to look at the load line, and okay, so it says load if one load memory to output, which means a 0 is a write operation. In other words, we are now selecting a write operation already. Okay, if this pin, if LD is getting a 1, it is specifying a read operation, reading from memory. If LD is a 0, it is specifying a write operation, writing to memory. So right now we are already specifying writing to memory. So what is left to do? The select line is already selected. In fact, the highlighting here already tells you that we are focusing on location 2C in hexadecimal of RAM 1. What is missing is the clock line. Okay, so when you hover over the clock line, it will tell you memory value updates on rise from 0 to 1. In other words, memory chips update on a transition of the clock line. When the clock line transitions from 0 to 1, that's when it will quote-unquote latch the content from the data bus onto a location in the memory. Is that okay? What is the value of the clock line at this point?
0.
It's a 0. So let's go ahead. I'm going to zoom out a little bit just so that we can see the effect of changing that line to a 1 while we can focus on this, okay? Oh, by the way, what is the value in hexadecimal? Go ahead.
Which bit from the processor is determining the select line? Is it the first bit or the last bit?
Is the most significant bit in this case. It's bit 8.
Bit, okay. But, so the 1 then, right?
The 1.
The top one.
The top one, right?
Is the most significant.
From the CPU?
That is correct, yes.
Okay.
Yep, it's the. This is bit 8. This is bit 8 here. Okay. All right, so what we want to do is we're going to change clock from 0 to 1, and I want you to focus on the highlighted portion here to see it change. But we want to know what it is supposed to change to first, right? What is it supposed to change to? In hexadecimal, because that's in hexadecimal. Remember, conversion from base 2 to base 16 is just a table lookup. 0110 is 6. 0010 is 2. So we should see the highlighted thing updating to 6.2. Okay. All right, so let's go ahead and do that. Voila. It updates to 6.2. And you have to clock the clock line can go back to 0 without changing anything, because once it updates, it doesn't do anything anymore. Okay? So this is how you write to a memory location. Let's figure out how to read from a certain location. Yep, go ahead.
So it's not incremental, so if you turn the clock back on, it won't change, it'll still be 62.
It'll still be 62. Yep. Well, let's try it. Okay, so let's change this to this number. Okay, this is a new value, and I'm going to write it to the same location. All right. So what you need to do is to have a rising clock, and it changes to E2. Because 1110 is E, it is actually basically 14, which is E in hexadecimal. Okay. All right. So let's go ahead.
Where is that right information coming from?
The right information
Yeah, so where's the 98 coming from?
from here.
But I mean, where is that attached to?
That is also attached to the CPU, the processor. But I don't have a processor because I'm demonstrating how to use the memory module on its own. But those pins, okay, this pin, all of those, and that eventually will connect to the processor. Everything goes back to the processor. All right. So I think we still have enough time to demonstrate how to read from a location. Okay. Now, reading from a location means we have to use the other pin, the one with rounded corner, because those are the output pins, because we are reading from memory to the output. So you can hook up this and it's fine, okay? You can see that it is actually reflecting the value of that bus, okay, which is fine. Now is a good question to ask: who is driving the bus? Not literally driving, but who is determining the value of the address bus? Out of all the components on the screen right now, which component is determining the actual value of that bus? Nope, not the decoder. The input pin, the square thing, this one. This is actually what is driving the bus. Next question: how many things can drive the bus at the same time?
1.
1. Yes, exactly. So if you take what the regional transit, RT, you don't want to have like 3 drivers competing for the steering wheel, right? So let's go ahead and create that scenario by using a read operation. Let's go ahead and do it. Let's have a bus fight. And that's not a, you might think it's a funny term. It is actually a technical term, okay? If you look up your bus fight, in electrical engineering, that actually has meaning. It's exactly what we're gonna do next, okay? So what we want to do is to read from a certain location, and we want to do something that's a little bit different. Let's go to this location here. You can right-click on the RAM module and click Edit Contents. And that will allow you to go to a particular location. All you have to do is to type something here. Okay, I'm going to just type 7D and change that location to 7D and close the window. Whoops. Yep, there you go. So 7D is now this location. This is, by the way, location 1 of the entire memory area, right? Because it belongs to RAM 1 and it's location 1. So that's good. It's easy to do. All we have to do is to now change the address bus to specify that location. Turn everything into zeros except for the least significant bit, and now we're addressing that particular line. But when you look at the load line, what is load specifying? LD. It's still specifying 0, which means we have a write operation pending, okay? But until we clock the clock line, nothing really happens. So let's see what happens when I flip LD from a 0 to a 1, because a 1 on the LD line means we are reading from memory. Now what happens when I'm reading from memory? What component should be driving the data bus? The memory chip, right? Because if I ask you and say, tell me what is the content of page 64, who's going to talk next? The memory chip, right? Yep.
So when you say read, that means we're taking the information from RAM 0 and sending it out of port D.
We are taking the information from location 1 of RAM 0 in this case, and the processor is supposed to be listening. But what is the processor doing right now? It is also driving the data bus. So when I flip LD to 1, I end up with a bus fight. This is what we call bus fight. It's literally called bus fight, okay? Because now we have 2 components driving the data bus. The first component driving the data bus are these, quote unquote, is this pin here, okay? Because an input pin means, you can use the input pin to determine the value of the wires, the individual wires. But at the same time, because this is a read operation and this chip is already selected, it wants to tell the entire world through the data bus that the content of this location is 7D. So now we have bus fight, and the result of a bus fight is blah, 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 blah. Okay?
Spell that.
Yes. I would like to see how the automated captioning is going to do with this one. Huh? Okay. So a bus fight ends up with random values, okay? Basically random values. But it can do a lot worse, because what's happening is if one side is driving a 1, okay, this side is driving a 1 with the most significant bit, but the memory chip is driving the same pin low, okay? The processor is driving it high, the memory is driving it low. What happens? Driving high means you're pumping current into a wire to raise the voltage of that wire to a higher voltage. Normally, it doesn't take much, okay, because there's not much load on the line, so it doesn't take much to change the voltage from low to high. What does it mean when you're trying to drive low? You're trying to you're trying to drain current from that wire so that the voltage of that line drops to 0. And normally, it doesn't take much because there's nothing, that is actually fighting that attempt. But what happens when you have one component driving high and the other component driving low? Then you have a short circuit, because one component is trying to source current, just trying to pump out current. The other one is trying to suck or drain current, and there's nothing stopping them in between. So it will just be limited by how much the chips can actually pump and drain. Okay? What do you think current means to chips? So let me go to a particular physics equation in electrical stuff. Power is current times voltage. Okay? We just bump this up a whole lot. Okay? So what does it mean? There's also a lot of power involved, right? So what is that power doing to your computer?
Burns these.
There's energy. It has to be conserved, right? You cannot create or destroy energy. Well, not when you're talking about computers. Okay, if you're taking an astronomy class, maybe there are ways to do it, but not in this class. So that power has to do something, right? What is it doing?
Rise to releases of heat.
Exactly. It is all converted into heat. Okay, and what is it heating up? The two components that are fighting. Okay. And then you will say, that's going to be okay. See, the memory has got a big old heat sink on it, right? And in some cases, if you have a gaming computer and you have high performance RAM, the RAM chips also has its own little heat sink. So you go like, it can handle that. Yes, overall speaking, it can handle it. But remember, we're talking about tiny little transistors here. It doesn't have enough conduit to dissipate this kind of heat to the heat sink. So what happens?
Meltdown.
Well, it won't even melt down, because if it did melt down, it would be easy to fix. You can see what is damaged. It would just destroy those particular transistors within the component, and it won't work anymore. That's it. That's from the outside. You will not see any evidence that it is destroyed because of a bus fight. Yep.
Can the same thing happen to the processor in the of that relation? Like when the
Yes.
drivers.
If you wire up or misprogram your processor, this can happen too. So what it means is this, okay? When you are reading from memory, this has to be disconnected. This wire has to be disconnected because the processor has to be in listen mode and not in talking mode. In other words, if I ask you, for the content of page 26, okay, right after I say, okay, tell me now, I have to shut up. Because you'll be talking and tell me, oh, on page 26 I have blah, 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 blah. But if I keep talking and yakking all along, there'll be a bus fight because we are all talking at the same time, right? So how do you stop the processor from talking? Just take out this wire. So now it has the input pins are now disconnected. They mean nothing now to this diagram. But the output pin is now reflecting what the RAM is reading from location 01 is 7D. Is that 7D? 0111 is 7. D is 1101. Yep.
Why will it not read from RAM 1?
Because the actual location I'm trying to read from is 000001 in the logical space. That belongs to RAM 0. Okay?
Well, isn't it also because we have the input to the decoder at 0, so it's going to select that?
But the input to the decoder is 0 only because we are reading from logical location 1. Because this 0 eventually goes here.
Yeah.
Yeah. All right. So we are running out of time today. You are more than encouraged to do something like this. One, it will help you get more familiar with the tool itself, and two, you can run your own experiments just to find out how to read from memory, how to write to memory, and so on. This is the foundation of what is yet to come in this class. Okay, so I'm going to stop the lecture at this point so the next class can come in. And
Load this up to Moodle.
yeah, well, I was debating whether to do that or not, because I think you guys should be able to do it yourself.
Okay.
Yeah. Stop the recorder.